Hi, it's Moser with yet another quick tutorial on Lewis structures. This time, Lewis structures which require resonance structures. Huh? So after this video, you should be able to define resonance as it relates to molecules and polyatomic ions that contain double bonds. You should be able to correctly identify when a molecule or a polyatomic ion requires a resonance structure, and you should be able to draw Lewis structures showing resonance. So you already need to know how to draw Lewis structures involving multiple bonds using that old octet/valence math, sometimes referred to as Gooch math since I stole it from Mr. Gooch. Let's get started. We're going to start off with our old friend ozone. That's just three oxygen atoms bound together to form a single molecule. And it's found in the upper regions of the atmosphere where it's a really good thing, and occasionally down here at ground level where it's not a good thing. We're going to start as we always do by listing the type and number of atoms, pretty easy in this case, and figuring out how many valence electrons each of them bring to the party. We'll then figure out how many electrons they would need to be satisfied, their octet numbers, and when we subtract valence from octet, we get the number they're sharing. In this case, 24 octet minus 18 valence gives us 6 shared electrons. The number of shared electrons divided by 2 will tell us how many bonds we need, and that tells us we're looking for 3 bonds. While we're at it, we might as well figure out how many unshared electrons we're going to have. So valence minus the number shared gives us unshared, and in this case, we will have 12 unshared electrons. So this seems easy enough. I mean, what goes in the middle? Gee, I don't know, oxygen, or should I put oxygen in the middle? Yeah, exactly. So I've got 3 oxygens. They're strung out like this, and I have 3 bonds. Well, okay, that clearly indicates that I would have to have a double bond and a single bond. This is not so hard yet. I don't know what the big fuss is, Moser. Well, where do I put the unshared pairs? This is where we have to think about the octet and what constitutes an overloaded atom. Well, this oxygen out here, 1, 2, 3, 4, 5, 6, 7, 8, would be satisfied with 3 unshared pairs on it because it's not over 8. Now, on the other hand, this oxygen on the other end over here already feels like it's got 2, 4. So it can only take 4 more unshared pairs. So we're going to put 4 right there. Now this middle oxygen feels as though it is surrounded by 6 electrons. Kind of crazy, huh? So it can only handle 2 more. Now, let's do our quick check in terms of octet satisfaction and the number of valence electrons total. First, we'll check total number of valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18. Hey, we're good. Now, let's check each individual atom to make sure they're satisfied. We've kind of already done this. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Great! Everybody's happy. We're done! Wait, no we're not. So here's my question for you. How do you know that the double bond goes there? How do you know it doesn't go there? How do you know this thing doesn't look like this? Huh? Well, that's exactly the point of this video. What we're running up against is a situation where we need a resonance structure. So it turns out that there are some molecules that just can't be represented by a single Lewis structure or a single structural formula. And ozone is a classic example. We don't actually know if the double bond is here or here at any given moment. We don't know if this oxygen is carrying 2 unshared pairs and this one carrying 3, or vice versa. Well, what chemists have found in more recent years is that it's not an either-or situation. The entire electron density kind of gets shared out, so the molecule exists, well, sort of in this weird middle. Well, when we have a situation like that, we have to use a resonance structure, which means we have to show the structure of this atom, or this molecule rather, with the double bond in every position that it could possibly be in. And we then put a little double-headed arrow between them, kind of to say, yeah, it goes back and forth. It's somewhere between these two. So let's do that with the ozone that we just finished. That's it. Wow, that's easy. Okay, cool. Notice that there are no brackets or anything around this unless it's a polyatomic ion. The only thing we have to do to show resonance is to show the structure for the double bond existing in any of the places it could exist and to put a double-headed arrow in between those representations. Excellent. Let's move on and try another one. Okay, so I've got NO3 1-. This is the nitrate ion. You'll come to know it very, very well later as it's a polyatomic ion that participates in all kinds of reactions. But to start off, we're going to go ahead and draw the Lewis dot diagrams for the molecules as they would, or the atoms as they would appear on their own. And then I'm going to list the types and number of atoms I've got. And here I'm going to write a reminder to myself that I have one extra electron because this is an anion. So I'll figure out how many valence electrons this little structure brings to the party, and then how many octet electrons, or how many electrons would be required for everything in this polyatomic ion to be satisfied. My valence number is 24, and I get an octet value of 32 electrons. Great, I know that octet minus valence equals number shared, and in this case, 32 minus 24 gives us 8 shared electrons. Number of shared electrons divided by 2 will show us how many bonds we're looking for, and in this case, we're looking for 4 bonds. Might as well go ahead and figure out how many unshared electrons I'll have. The number of valence minus the number shared equals those that are unshared, and we have a whopping 16 unshared electrons here. Well, let's get started. So first of all, I have to figure out what's going to go in the middle. And we know that it's carbon if carbon's present, or the least electronegative element there is. Oxygen's more electronegative than nitrogen, so we're going to put nitrogen in the middle. And if you didn't remember that, you can also look at it and say, there's one nitrogen, there are 3 oxygens. I bet the one there's only one of goes in the middle. It does. So I know that I have these 3 oxygens, and I know they have to be bound to hydrogen at least once. So I'll go ahead and put a single line from each oxygen to the nitrogen, but that only gives me 3 bonds, and I know I need 4 bonds. So that means I have a double bond. Oh, interesting. Now, I also know that I have 16 unshared pairs, and if I look back at our oxygen and how it started off, I think it's unlikely that oxygen shed those extra electrons. As a matter of fact, not only did nothing in here shed those extra electrons, we picked up more electrons from out there in the world. So how many unshared electrons can I put on each oxygen? Well, again, I always have to think in terms of octet. 2, 4, 6, 8. Cool. 2, 4, 6, 8. Excellent. Now, what about that oxygen that's double bonded? Well, it already feels like it has 4 electrons on it, so it's only going to get 2 unshared. Hey, fantastic. Oh, wait, what did I forget? This is a polyatomic ion, so it gets a bracket with its charge listed outside. But wait! How do we know the double bond's here, and not here, and not here? Yeah, we got to do resonance. Well, that is the whole point of the video, isn't it? So, sure enough, I am going to show this nitrate ion with the double bond in every possible location. Since there are 3 places it could be, guess how many little resonance structures I have to show? Oh yeah, you guessed it, 3. What a pain in the tuchus. Hey, guess what? We've covered all the possibilities. We have shown the double bond in this position, and this position. Let's double check and make sure that we haven't sort of overloaded any of our oxygens. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Yep, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Excellent. They've all got the correct number of electrons surrounding them. They're all shown in brackets with a charge, and I've put my little, badly drawn, sorry about that, double-headed arrows between each of the resonance structures. That's it. just remember, anytime you have a double bond that could exist in more than one place, you got to show it existing in more than one place. Now, let's do one sort of common misconception check. Let's look at cyanide. Remember cyanide? We used cyanide as an example of a compound with a triple bond. Do we have to show resonance for cyanide? Could this triple bond exist over here? Ding, 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 ding. That's the Jeopardy theme music in case you didn't get it. Could it? No. Hydrogen can only bond once. So there's no way that we could have hydrogen triple bonded to carbon, single bonded to nitrogen. That's crazy. Carbon's satisfied, but hydrogen's overloaded and nitrogen's starving for electrons. So be careful. You only need to show resonance when there is legitimately more than one location in which the multiple bond can appear. Okay, practice, have fun, happy chemistry.